fix the mistake that I made in your class today. So first,
I really appreciate it.
come back. I have the bit of notes here. I looked at it for just a second after class. Here was the problem. Our work with f prime is fine, but when it came to f double prime, I made a mistake.
Okay.
And the mistake is, I'll show it in blue. Here, these two minuses come together to make a plus here. But on my next line, I wrote it as a minus. That's the fuck up. So this should have been a plus here, not a minus. But there's a better way to do the algebra. And I've got that down here. I'm going to go through it step by step for you, but this is the result. So if you force factor an x to the negative 5/3 from this expression, you'll get x plus 2. And I'll show you why. So I want to run back through that whole problem. That way I can post this to Canvas later with the full video. So if it's okay with you, let's do this from the start. Is that all right?
Yeah, go for it.
Okay. So this is a correction. For Calc 1 on 7/20. We wanted to sketch f of x, which was parentheses x minus 4 times the cube root of x using derivative info. All right, so this got out of hand pretty fast because the derivatives are a little bit nasty and involve negative powers of x. I absolutely will. Oh, Caesar's asking me to upload the previous one to Canvas. I didn't start recording until just now, Caesar, so I don't have that one recorded, but I can try to maybe upload a few other problems. Send me in chat other stuff that you would like to see and I'll upload it. All right. F prime. We're using the product rule. So I need to differentiate x minus 4 times x to the 1/3. And you don't have to use a product rule here. You could distribute this and then differentiate straight up, but I'll do it as the product rule because that's how I did it in class. I differentiate x minus 4. His derivative is 1, and I leave x to the 1/3 alone. And then I add that to what I get when I leave x minus 4 alone and differentiate x to the 1/3. That's 1/3 x to the negative 2/3. And then I distribute. So this is x to the 1/3 plus 1/3 times, and then I'll have my x minus 4 over x to the 2/3. And then we could have a common denominator, and this is how we did it in class. So I multiply this by x to the 2/3 over x to the 2/3, and I get x to the 2/3 times x to the 1/3 over x to the 2/3. Plus, here I'll just bring that 3 downstairs, so that's going to be x minus 4 over 3 times x to the 2/3. The last thing I need in order to make the denominators the same is a 3 over here, because I've got a 3 here coming from this 1/3. So 1/3 upstairs is the same as a 3 downstairs, so I just move that 3 down here. So I'll multiply by 3 over 3 in the first piece. Now this, x to the 2/3 times x to the 1/3, is the same as x to the 2/3 plus 1/3. And that's x to the 1. So this is 3x from here plus x minus 4 from here, all over 3x to the 2/3. So that's 3x plus x is 4x minus 4 over 3x to the 2/3. So my critical numbers the places where f prime is 0 or undefined are places where the top is 0. So 4x minus 4 will be 0. If you factor the 4, you'll see that that's the same as 4 times x minus 1. So the top will be 0 when x is equal to 1. And the bottom is 0 when x is equal to 0. And remember, I'm not going to go back through all the domain work we did for this, but the domain of this function is all real numbers. The domain of the original is all real numbers. So we include the 0, right? Remember, critical numbers are anywhere that f primed is 0 or undefined, but the numbers also have to be in the domain of the original. F double primed is where we ran into trouble. So I need to differentiate this thing. I'll write that as 4 over 3 times x minus 1 over x to the 2/3, all primed. And then just like I did in class, I'm going to take this x minus 1 over x to the 2/3 and split that up as, so I'll bring the 4/3 out. Constant multiple comes out of derivatives. That's x over x to the 2/3 minus 1 over x to the 2/3. You can split fractions up over their numerator, that works fine. Now I simplify, and I still need to differentiate, so the prime. This is x to the 1 over x to the 2/3. So that is the same as x to the 1/3. So up front, I have my 4/3. This is x to the 1/3 minus x to the negative 2/3, and we need to differentiate still. So I still haven't done any calculus for f double prime, just algebra to get it into a form that's easier to differentiate. Now on this next line, I'll do the differentiation. The 4/3 popped out because it was a constant multiple. The derivative of x to the 1/3 is 1/3 x to the negative 2/3, because 1/3 minus 1 is negative 2/3. The minus here is the minus here, and then the negative 2/3 will come down. And if I subtract 1 from negative 2/3, I get negative 5 over 3. So this is 4/3 times 1/3 x to the negative 2/3 plus 2/3 x to the negative 5/3. And there's a bunch of ways to clean this up. But what I'd like to show you here is a neat trick, because expressions like this are fairly common in calculus, and you don't always want to have to do this common denominator thing. You saw in class today, I messed this up when I did it for this guy. So there's a faster way to get from an expression like this, that is an expression like this, to an expression like this. And the fast path, rather than going through that common denominator stuff, is to force factor the largest negative power of x. So first, let me bring out the 1/3. That'll make this a 4/9. I'll leave everything else the same. And then I'll have x to the negative 2/3 plus 2x to the negative 5/3. And the trick is to force factor the largest negative power. So the largest negative power here is definitely the 5/3 power. That's more negative than negative 2/3. So I'm going to force factor him out. So I'll have 4 over 9 times x to the negative 5 over 3. And then let's see what's left inside if I do that. Over here, I'll just have plus 2 because this is what I'm factoring out. So this is what will be left. If I take x to the negative 2/3 and I want to divide out by x to the negative 5/3, I will have x to the negative 2/3 minus negative 5/3. Remember, factoring is division. When I factor out x to the 5/3 or x to the negative 5/3, I'm dividing this whole expression by x to the negative 5/3. If you want to divide x to the negative 2/3 by x to the negative 5/3, that means you're subtracting the powers. So I'll have x to the negative 2/3, the first power, minus negative 5/3, the second power. And this cleans up so nice. I haven't shown this to you guys because we haven't really needed it yet. But today we got to a place where we really did have some algebra that's nasty without this trick. So negative 2/3 minus negative 5/3 is negative 2/3 plus 5/3. That's x to the 3/3, which is x to the 1. So I'll write it as 3/3 for now. But 3/3 is 1. So this is 4/9 x to the negative 5/3 times x plus 2. And this was my fuck up. In class, what we did was equivalent to having a minus here. It should have been a plus. So here's f double prime. So places where f prime prime is equal to 0 or undefined are going to be at negative 2 from this factor and 0 from this factor. This factor really belongs downstairs. If you want to write this as a neat fraction like we have there, it's 4 times x plus 2 over 9 times x to the 5/3. So if you wanted a fully simplified second derivative written as nicely as possible, it's this. And the fastest way to get there once you get here is to force factor the largest negative power of x out. So I factored x to the negative 5/3 out. This is what was left. It simplifies to this. So we're undefined when this bottom term is 0. This bottom term is 0 when x is equal to 0. Finally, f itself is equal to 0 at 4 and at 0. So f of x equals 0 at x equals 0 and 4. So when I go to make my number lines, the number line for f will have 0 and 4. The number line for f primed will have 0 and 1. And the number line for f double primed will have 0 and negative 2. I'm going to go ahead and make those number lines now. Number line for f has 0 and 4. Number line for f primed, which was 4x minus 1 over 3x to the 2/3. This number line had 0 and 1. And f prime primed, which in its most simplified form is 4 times x plus 2 over 9 times x to the 5/3, should have negative 2 and 0. I'm not really worrying about the spacing relative to each other on these number lines. I'll just do each one on its own. If you plug a negative number in here, like negative 1, if you test x equals negative 1, you'll get negative 1 times negative 5. And you'll get negative times positive. You'll find that that is, did I say that right? Negative 1. Cube root of negative 1 is negative 1. negative 1 minus 4. So I'll write it, why not? F of negative 1 is negative 1 times negative 5 is definitely positive. As you jump over the 0, you will change sign because the cube root of x does change sign at 0. Picture just the graph of cube root x on its own. He goes from negative to positive right there at 0, so he will change. Or you could test x equals 1. F of 1 is 1 times negative 3, which is definitely negative. And then if you test 5 or 8, F of 8 is the cube root of 8 is 2 times 8 minus 4 is 4. That's positive. So F goes plus minus plus. F primed, if you test negative 1, you'll get 4 times negative 2. So F primed of negative 1 is 4 times negative 2 divided by 3 times negative 1 to the 2/3. That's negative 1 to the 1/3 all squared, or the cube root of negative 1 squared, which is positive 1. So that's negative 8 over positive 3, that's negative. If you test something between 0 and 1, like 1/2, F primed of 1/2 is 4 times 1/2 minus 1 is 1/2. Sorry, negative 1/2. 1/2 minus 1 is negative 1/2. All divided by 3 times 1/2 to the 2/3. So again, I don't care about what this is. I just care about whether it's positive or negative. The top is negative. The bottom is positive. So we're negative here. Or if you like, because of the 2 right here, I can think of the factor downstairs as kind of being similar to an even multiplicity factor. So I won't change sign as I jump over the number that comes from him. And then if you test x equals 2 over here, or any number bigger than 1, I'll test 8 again because 8 is a perfect cube. F primed of 8 is 4 times 7 over 3 times, what is 8 to the 2/3? Well, I take the cube root and then I square it. The cube root of 8 is 2. 2 squared is 4. So 4 times 7 over 3 times 4, it's positive. So F prime goes minus, minus, plus. And then F double prime, this is the one I messed up in class, shouldn't have had 0 and positive 2. It should have had negative 2 and 0 because of that sign error. So again, if you're looking in your notes, I would like to draw your attention to the mistake, which was here. The mistake in class, these 2 minuses made a plus, and I wrote that correctly. But then on my next line, I wrote it as a minus. Big mistake. That's where our trouble came from. So if you're looking in your notes and you want to go back and try to correct, change this minus to a plus. And then you can follow from there, and everything will work out just fine. But I would prefer, or I would suggest, going back through it as I did just a second ago here. So go back to the start of this video and you'll see it. The factor that we are able to sneak out of the thing is x plus 2, not x minus 2. So negative 2 is our number for the number line there. So we need to test something to the left of negative 2. I could test, again, I want it to be a perfect cube to make the bottom nice. So I'll test x equals negative 8. F double primed of negative 8 is 4 times negative 8 plus 2 is negative 6 over 9 times, if I take negative 8 and I take the cube root, that's negative 2. Negative 2 to the 5th power is negative 32. Top and bottom are both negative, so F prime prime is positive over there. between -2 and 0, I can test -1. F prime prime of -1 is 4 times 1 over 9 times -1 to the 5/3. The cube root of -1 is -1. -1 to the 5 is -1. So this is 9 times -1. So the top is positive, the bottom is negative. We're negative here. And if we test +1, f double primed of +1 is 4 times 3 over 9 times 1 is positive. So these are my 3 number lines for f, f prime, and f double prime. In summary, I'll have -2 over here, then 0, then 1, and then 4. And in each of these regions, I want to say whether I'm increasing or decreasing, concave up, concave down, all that stuff. So is f positive or negative? Yeah, go ahead.
Where'd you get the 4 from again?
The 4 is a place where f changed sign.
Oh, okay. I see. I didn't see that up there.
Yeah, all the way at the top.
Okay, thank you.
So from -∞ to -2, f is definitely positive because f is positive everywhere to the left of 0. F primed is definitely negative because f primed is negative everywhere to the left of 0. And f double primed is positive. So over here, f is greater than 0, f primed is less than 0, and f prime prime is greater than 0. So over here, we are f of x is positive because f itself is greater than 0, decreasing because f primed is negative, and concave up because f double prime is positive. Between -2 and 0, f is still positive. F primed between -2 and 0, we're still to the left of 0, so f primed is still negative. But between -2 and 0, f double primed has changed sign. F double primed is now negative. So f of x everywhere in this region is positive, because f is positive, decreasing, because f primed is negative, and now concave down. Because f double primed is negative. All right. So f being positive means f is positive, nothing special there. F prime being negative means f is decreasing. And f double prime being negative means f is concave down. In the region from 0 to 1, f itself is negative. F primed between 0 and 1, also negative, right? Am I seeing that right? Yeah. And f double primed becomes positive. So f of x is negative. F primed is negative, so f is decreasing. And f double primed is positive, so f is concave So I've got an IP here where I go from concave up to concave down, and I've got another IP here where I go from concave down back to concave up. Two more regions to fill out. To the right of 1, f itself is still negative because from 1 to 4 is definitely in here between 0 and 4, so f is less than 0. F primed, I'm looking between 1 and 4, f primed is positive because f prime becomes positive at 1 and stays positive. And f double primed between 1 and 4 is positive, right? F double prime changes sign for the last time at 0, never changes sign again. So we stay concave up. So f of x is negative, increasing, and concave up. And then finally, to the right of 4, f is positive, f primed is positive, f double primed is positive, all positive. So f of x is positive, increasing, and concave up. So here is my summary number line with all the information from the 3 pre-existing ones. I can use this to draw the graph. I'll mark maybe -1 and -2. So it would be 1, 2, 3, 4. My end behavior, remember, is up on both sides. That's not exciting. But at -2, I had an inflection point. Because at -2, right here, f goes from, so we're positive, positive, decreasing, decreasing. Oh, but concave up, concave down. So there's an IP, an inflection point at -2. So I need to find the y value. F of -2 is, what was f of x? F of x is x minus 4, so that's -2 minus 4 times the cube root of -2, which is -6 times the cube root of -2, which is the same as 6 cube root 2, because negative, and then the negative cube root of -2 is negative also. So the negatives come together to make a positive. 6 cube roots of 2. Cube root of 2 is like 1.2, 1.3, somewhere around there. We know it's positive. We know it's smaller than 1. That's really all about we need. But if we want to be more specific, where's that? Desmos. A regular calculator. 6 times 2 to the 1/3. Yeah, it's a little bigger than 6, about 7.5. So my IP is at the point -2, 7.5, or my first IP. So maybe I'll mark this as like 10 up here, and this is like 5. So -2, 7 point some shit. I've got an IP right here. All right. That's at -2, 2 cube root 6. Moving on, the next point of interest is at 0. I know I have an x-intercept there. It's also my y-intercept. And what else is going on there? Well, f goes from positive to negative. Okay, so we're going to go from up here to down here. Decreasing to decreasing. Concave down to concave up. So I was concave up over here. Concave down here. And then I go from decreasing concave down here to decreasing concave up here. So I just draw little slivers that have the right behavior. Decreasing concave up, decreasing concave down, decreasing concave down, decreasing concave up. My next interesting event is at x equals 1. F is negative there. Increasing, okay, so I go from decreasing to increasing, and I stay concave up. So decreasing to increasing tells me that I've got a local min. So this was at 2, I had an IP. At 0, I had an IP. And at 1, I have a local min. And I need to find that y value. So I had another IP at x equals 0. F of 0 is 0. So the point here was just 0, 0, nothing interesting. I have a local min at x equals 1. F of 1 is 1 minus 4 times the cube root of 1, which is negative 3 times the cube root of 1, which is negative 3. So the point there is 1, negative 3. So if I use the same scale here that I did there, this would be like negative 10. This would be like negative 5. So 1, negative 3 is like right here. And I've got a local min, and it's a smooth local min rather than a sharp one. So we're concave up on both sides, but I go from decreasing to increasing. And then the next interesting thing that happens is all the way out here at 4, where I've got my last intercept. I know that f goes from negative to positive. We're increasing on both sides, and we're concave up on both sides. So this just looks like normal increasing concave up behavior. So now I can stitch these bits together and get a nice graph. Decreasing concave down, or sorry, decreasing concave up here, decreasing concave down here, decreasing concave up, switch to increasing concave up. We get the shape like that. So this was an IP at 0, 0. This was a local min at 1, negative 3. And this was just an x-intercept at 4, 0. Okay, so that's that problem reworked. And if we compare to what Desmos tells us, I think you'll find that this matches much better. We can rescale our axes, because right here they have the x and y scales set to the same. So if I scale this from like negative 10 to 10, and I scale this from negative 2 to 4, you see that same shape I have. Neat shit, right? It's hard to see the concave up behavior to the left, but if you really zoom out, you can see it. We're concave up here, and then right here at negative 2, we switch to being concave down. We've got our inflection point and our intercept here at 0. We've got our local min at 3 and our intercept at 4. So compare to this. All right. So that is the end of this. I am going to stop the recording because that is where I need to